Okay, so far we learned about the deep learning architecture and CNN architectures. Okay, uh, and previously I mentioned that between this input and output, any differentiable layers could be there. Okay, and if layers are individual layers inside the deep architectures are differentiable with respect, I mean, their output is differentiable with respect to their input and their parameters. They are called as differentiable layer. And each individual layers uh, constituted to consist of the deep architecture, then those deep architectures are becoming again differentiable. Okay, and for differentiable layers, we can apply the gradient descent algorithm to update their parameters. Okay. And the CNN, especially, they are the architectures, the deep architectures that stack multiple differentiable layers with some convolution operation. The C here in CNN, meaning the convolution operation, okay? And convolution is effective for processing the signals, okay? Especially image signals. The 2D convolutions are used, and that operation is effective for processing the 2D signals. At the same time, that's differentiable, okay? So convolutions, we will see that operation in detail in the later slide. That is composed of mainly plus and multiplication. Okay, because of that, their output is differentiable with respect to their input, and their output is also differentiable with respect to their parameters. Okay, and one more thing I want to add here is this is the deep architecture, and this is the input, and this is output, okay? And there could be multiple layers, okay? For example, let's say this is the output Y1, okay? And this is the second layer, this is the first layer, and this is the second layer, and this is third, and this is fourth, okay? So let's think about the deep architectures that is consisting of 4 layers, okay? And their intermediate outputs, we will call that as Y1, Y2, Y3. And also we will call their parameters, their layers parameters as sector 1, sector 2, sector 3, and sector 4, okay? And the thing I mentioned before is for this layer, we have to calculate 2 things for the differentiation of their output with respect to their input, okay? And also their differentiation of their output with respect to their parameter, okay? And also for here, we need these two, okay? Differentiation of their output Y2 with respect to their input Y1, and also the parameter sector 2, okay? Okay, and for here, we need this, okay? Are you guys agree with this? Okay, we need this 8 gradient for training the network. That's what I'm saying, okay, previously. But let's say for this layer, uh, let's say there's no parameter. Okay? If this parameter, if this layer, the third layer is not having any parameters to learn, we can simply will not count for this gradient, okay? So if some layers inside the deep architectures, if that layers are not having any parameters, then it's very simple case. We will not count for updating that parameters, okay? Are you guys understanding this? So even though in the intermediate layers, even though they have this, which is the differentiation of their output with respect to their input, they have this gradient, but if that layer is not having any parameter, then we can just skip this gradient. Okay. Okay. And eventually, the reason why we need this gradient is to further calculate loss L, right? That the loss is how to say, calculating some distance between our prediction with the ground truth y. Okay, I will call, yeah. For example, we normally calculate their Euclidean distance, or also we can use some other loss functions. We can define other loss functions as well. Okay? And also this loss calculation is normally constituted with multiplication and addition. So this calculation is also differentiable. So I mean, if the layers are differentiable until this final output y, then the loss L also become differentiable. Okay. And the thing we have to eventually calculate is this 3 gradient. Okay. If there's no sector 3, then we have to calculate this 3 gradient to apply gradient descent algorithm on these 3 parameters to update. Okay, are you guys understanding this? Okay, and I will show you how we can calculate DL d sector 1. Okay, so DL d sector 1 would be first calculate by multiplying this, okay, dl, differentiation of L with respect to y. And also then we have to apply, how to say, the differentiation of y with respect to y3, and also y3 respect to y2, okay? And multiply dy2 and dy1. And then finally, we will multiply this. Okay, are you guys understanding this? For I mean, to calculate the differentiation of final node L with respect to some intermediate parameters, the thing we have to do is multiplying the gradient. I mean that apply differentiation with respect to their output to input multiple times to transmit some signals. And then at the last part, we will multiply the output, differentiation of output with respect to their parameters, okay? So all of this part is for transmitting the gradient, okay? And at the final part, we will multiply the differentiation of output with respect to that parameter, targeted parameters, okay? So that's how we can calculate this DL sector 1. Okay, are you guys understanding this? And same for sector 2, right? Okay, and same for sector 4, right? So this is the chain rule. Are you guys understanding this? Okay. Okay. So this is valid when certain layers, if they do not have any parameters, right? Okay, so we can just omit that layer to apply the gradient descent. I mean, for this third layer, having this dy3, dy2 is sufficient for other layers to update their own parameters. Okay. Okay. Okay, and then from now on, we will see what 2D convolution operation is. Okay, so the convolution operation, maybe you may learn about this when taking the signal processing course, but maybe in computer science, maybe in that subject is in EE. So for computer science, if you have computer science background, maybe you will see this operation for the first time, maybe. Okay, 2D convolution, we need a two-dimensional input. Okay, so for example, here we are having 2D arrays, and normally we can assume the images are having two-dimensional array. Okay, and for calculation, we need to have filter corner. Okay, so what we will do is uh, when applying this 2D convolution operation for input image, we will apply this 3 by 3 filter color, and their dimension could be varied, okay? Depending on how you define this filter corner, it could be 4 by 4, 5 by 5, or others. And also you can define your own coefficients, okay? You can vary their coefficients, okay? And according to their filter corner shape, and also the coefficients itself, how the images are transformed can be varied. Okay? And anyways, what they do for this 2D convolution is they apply this 2D corner on the images. Okay, and also they pixel wisely multiply this coefficients inside the filter corner and the pixel values in the images. Okay, so this is the formula for that. So 1 is multiplied with 0, 1 is multiplied with 0, and 0 is multiplied with -1. Okay, so in this manner, they are multiplied and also added. Okay, and this becomes the output. Okay, and then you will shift the windows by 1 pixel right, and we'll do the same to calculate the next output pixel. Okay, and then you will shift again and calculate the next output pixel again. Okay, and if you reach the rightmost pixel, then the thing you have to do is making this go to the one row below and go to the leftmost, yeah, like this, okay? And do the same for calculate the next output, okay? And it iteratively done until you reach the right and bottom pixels, okay? Are you guys understanding this? Okay. And you can now feel that all the output pixels are coming from the input pixels by applying multiplication and addition with some other variables. Okay. So I mean the output of the 2D convolutions are differentiable with respect to their input signal and also the some intermediate variables. Okay. And this is the example for showing that the 2D convolutions are widely used for image processing. So for example, in Photoshop, you may see this image blurring effect, okay? So for image blurring effect, you can feel the coefficients of the filter corners as the uniform values. If you fill the filter coefficients as the uniform value like this, and then if you apply this filter corner on the all of the image patches in the input images, then the output patches will be like this because for example, these patches in the input images are multiplied with these uniform filter values, okay? And so somehow these patches will be, how to say, mixed. Their pixel values are mixed with nearby pixels, okay? Are you guys understanding that? So because of that, in human eyes, it is seemed as blood. Okay, okay. So this is how we do image blurring in Photoshop. This is image blur corners. Okay, filter. We normally call this as the blur filter. Okay, So this type of filters are called as blur filter. And if you do want to apply some sharpening, then you can apply different types of filter corners. Okay, so how you arrange these filter corners, your output images will be transformed from your input images. Okay, are you guys understanding that? So here in CNNs, what's the parameter sector? If someone else asks you what is the parameter sector to learn in CNN, then the answer is the filter corner coefficients. Okay, so we have to learn these coefficients to properly transform our input to the arrays. Okay, are you guys understanding that? Okay, so I mean, this is the CNN architecture composed of multiple convolutions and some of other pooling operation and fully connected layers, but mainly that is composed of the convolutions, and they are somehow transforming the 2D arrays into the form that is helpful for achieving our final tasks. Okay? For example, here we are wanting to achieve the image classification. Okay, we are wanting to classify these input images into some semantic labels and wanting to learn some helpful convolution kernels for that task. Okay. And also there are some other hyperparameters for 2D convolution operation. I'm saying that this is the hyperparameters because hyperparameters will not be learned during the training stage. Okay, the parameter sector, we will learn these values during the training. But if we say hyperparameter, then we will not train those hyperparameters, but we will preset these hyperparameters before training. Okay. So for example, 3 by 3, the dimension of the filter kernel, that is the hyperparameter. Okay. And also maybe image dimension, that is also be hyperparameter. And also we have to also define whether we will using the zero padding or not. Okay. Zero padding means, I mean, applying some padding around the original image. Okay. So mainly this zero padding is done to decide the output dimension. Okay. So I mean, somehow the output dimension of the 2D convolutions are automatically decided based on the dimension of the image dimension and also based on the filter kernel size. Okay, are you guys agree with that? Okay, uh, but I mean, if we do not use any zero padding, you can see from the 5 by 5 sized images, if we apply 3 by 3 filter kernel, then their output size is slightly reduced from the original image size. Okay, that's inherent characteristic of the convolution operation because, I mean, starting from this and the number of how many filter kernels you can apply, that becomes the dimension of the output, I mean, pixel output dimensions, okay? So it is somehow controllable by by controlling the other hyperparameters, and one of those things are zero padding. And zero paddings are first proposed to retain the dimension of the input in the output space. Okay, so for example, for 5 by 5 size image, we can apply, if we do zero padding, then we can start our convolutions from these pixels rather than from these pixels. Okay, are you guys understanding that? So without zero padding, we had to start our convolution operation from this. Okay, but here, because there are anyways the zero pixels around the images, we can apply convolutions from this part, okay? Because of that, the number of convolution operation we can secure is becoming larger, and thereby we can secure the dimension of the output larger, okay? And if we apply one zero padding and if we use 3 by 3 filter corner, then the output will be same as the input images, okay? Are you guys understanding that? So, I mean, this zero padding is used to control the output size, okay? Okay. Mm. So this is some formula for, I mean, how many zero padding is required to obtain the original, retain the original input image size, okay? And also there are some hyperparameters called as stride. Okay? Stride means previously I mentioned that we will move this corner window by 1 pixels to the right. Okay, but if we, I mean, the stride was 1 for that situation, and if we increase the stride value, for example 2, then now the windows will be moved by 2 pixels. Okay, are you guys understanding that? Okay. Then if we increase the stride, again, the number of convolution operation will be reduced. And then, I mean, if we use stride as 2, then the dimension of the output size will be halved. Okay. Are you guys understanding that, right? Okay. So this is another hyperparameters in convolutions, okay? So stride and zero padding that can control the output size, okay? Okay. I mean, because 2D convolutions, those are already differentiable operation, the remaining thing is controlling the dimensions, okay? The design choices are remained for us, and the main choices will be how we can set this stride and this zero padding and also the filter corner size. That's the choice we have to make when building the new architectures. Okay? And that was a 2D convolution operation, but we are using these 2D convolutions to build the convolutional layers. Okay, I mean the actual convolution layer inside the CNN is slightly different from the original 2D convolution operation. Okay, but I mean that's simple. Okay, so this is showing the input layers. For example, we may have 3 channeled images because we are normally using the RGB, the color images. Okay, so for example, here we have to have this dimensional input. Okay, for example, the height would be 5, width would be 5, and 3 would be the channel number. Okay, and then how to say, we will apply 3 different filter corners. Okay, we have to define 3 different filter corner. Okay, and I mean that one operation, one convolution operation, you have to apply this filter corner on this input image to get this output channel. Okay, and then the thing we have to do is we will add these I mean 3 different channels. We, how to say, pixel wisely add their pixels, okay? And then we'll get the first output channel. Okay? Are you guys understanding that? So for each input channels, we will apply 3 different corners, and this would be the intermediate output, okay? And then we will add them together to define the first output, okay? And then we will apply different corner again, and we'll get the different intermediate output channels. and then we'll add them together to define the second output channel, okay? And we can define the third by defining the another three different filter corners, okay? And we can define n number of output channels by iteratively doing that, okay? Are you guys understanding this? Okay. I mean, the n here, we can define by us, okay? We can define the number of output for the convolutional layers, okay? Are you guys understanding that? I mean, the only thing is we by defining more layers, more output channels, then the thing we have to do is to define more filter corners, okay? So anyways, we can control the number of output channels, okay, in convolutional layers. And you can also now see all the operation here is constituted with plus and multiplication, okay? And the output channel that is differentiable with respect to the input channel at the same time respect to this parameter sector, which is the filter corners. Okay. Are you guys understanding that? Yes. So this is how we proceed the convolutional layers from the input to the output. Okay. Okay. And another important layers in the CNN architecture is called as the pooling layers. Okay. The pooling mainly does reducing the dimension of 2D signals. Okay, reduce 2D to one-dimensional signals. Okay, so CNNs they are using the two-dimensional images as input, but using CNN, we eventually have to map them into one-dimensional vector that denotes the probability for n classes. Okay. So inherently in CNNs, we are wanting to reduce the dimension of the 2D signals. Okay. And in practice, in experiment, especially in the AlexNet, which is published in 2012 in Europe, uh, I mean, reducing the dimensions are not losing many information, but instead they confirm that it can retain only informative informations in the pixels, okay? And thereby they are finding that applying pooling can improve the performance, okay? They are not losing much information, but instead retaining only the informative pixels, okay? So pooling is wanting to reduce the dimension of 2D signals. And how they do that is, for example, there are multiple types of pooling, but we will see two types of pooling, max pooling and average pooling. Okay? That those two are widely used techniques for pooling. Okay? And here, what they do, I will explain max pooling first. This 4x4 input array, 2D array, we have to, here also there should be some hyperparameters, and stride have to be 2, and filter corner, normally we use 2x2 or 3x3, okay? And what for this setting, what they do is, because their filter corners are 2x2, they are, the filter corner looks like this. Their width is 2 and height is 2, okay? There are 4 pixels inside this filter corner of the max pooling, and they are moving by 2 pixels because their stride is 2, okay? Are you guys following that? Okay. And for each window, what they do is they have to choose 1 pixel that is maximum. So for example, here in this box, 6 is the maximum pixel, okay? So 6 is chosen, and And here, this 2D box is shifted by 2 pixels like this, and choose the maximum value, which is 8, okay? And 8 is selected here. And again here, the maximum value 3 is selected. And again, the 2 pixels are moved, and 4 is chosen, okay? This is how the max pooling works, okay? And the important thing here you have to remember is this pooling operation is also differentiable, okay? So, even though the operation is retaining one maximum values for among the windows, you can interpret that as multiplying zero constant to other values and multiply one to the maximum value, okay? And these somehow masks are retained during the training. If we retain these masks during the training, this operation is becoming differentiable, okay? So our output is 6, okay? Because all other values are multiplied with 0, okay? We only retain the path to this, okay? So, this is operation to select the max pooling, and only the gradient will be flow in this path. Okay, 6 paths, 8 paths, 3 paths, and 4 paths. Okay, and the previous layers will get some gradient from these maximum values. Okay, so if you think this carefully, you can realize that this pooling operation is also differentiable operation. Okay, and the other important pooling operation is average pooling. Okay, and this works like this. So from this window, we can average 4 values to get this 13. And next window, you can average these 4 values to get this 8. And next window, you can average those to get this 79, so on, okay? This is another way to reduce the 2D signals, okay? And also, of course, this is differentiable, okay? We apply average operation, which is constituted with addition and division, okay? So output, average pooling, their output is differentiable with respect to their input, okay? And also you have to remember that there is no parameters to learn for this pooling operation, okay? There is no parameter sector to learn in this pooling operation, but the only thing for this type of layers, which is not having any parameters, the thing we need is gradient that transmit the signals to the output to the input. Okay, the differentiation of output to the input. If that is defined, then the previous layers could get gradient. Okay, and can be learned. Okay, so pooling is anyways used to reduce the 2D signals to the one-dimensional signals, okay? And there are many, many types of pooling operation, okay? Choosing some value out of multiple values, but in practice, max pooling, average pooling, those two are widely used because of their good performance, okay? And the other important operation is activation layer. Okay, activation layer. You will further see why this activation is required. During inside the deep architectures, you will see that clearly maybe in the next class. Okay, but in this class, you please be familiar with these three activation layers, okay? That is also called as non-linear layer, okay? I will show that if you do not use these non-linear layers inside the deep architecture, the entire deep architecture will become the huge linear operator. Okay, I will show that in the next class. But anyways, in this class, please be familiar with the operation, detailed operation of that. Okay, so linear and nonlinear. I slightly told about that in the first class. Okay, but linear, that's defined like this type of linear equation. The power of x is less than 2, less than 2, which means just 1. Okay. But nonlinear layers, if power of x is more than 2, more than or equal to 2, then we normally call that as nonlinear functions. Okay. And their graphs are involving some curve. Okay, so this is just straight line, but if the power of x is larger than 2, larger than or equal to 2, their graphs are becoming to have curve. Okay, and if you see the activation functions of this, actually that is called as sigmoid functions. Okay. You can see their graphs looks like this, and you can see they are having some curve. Okay, that is proving that they are nonlinear functions. Okay. Anyways, and sigmoid, the thing you have to remember is their x values are defined from minus infinity to infinity. Okay, their x is defined from minus infinity to infinity, but you have to remember that their y values are defined from 0 to 1. Okay, their y values are bounded to uh, 0 and 1. Okay, that's the sigmoid function. Okay, and tangent hyperbolic, you also have to remember that their x values are defined from minus infinity to infinity, but their y values are bounded to minus 1 to 1. Okay, and also you can see there are some curves, and this is also some nonlinear functions. Okay, and the other nonlinear functions, which is widely used nowadays, is called as ReLU functions. Okay. And actually, there are improved version of ReLU because ReLU has some issues. So there are some improved version of ReLU. But I mean, ReLU is, I mean, the one of the successful nonlinear functions, which is widely used in CNNs. Okay, so actually, in the year of 2012, the main switch from the previous CNNs, which has some issues, to the successful CNN proposed in 2012 was one of the important advancement was using the ReLU, okay, instead of tangent hyperbolic or sigmoid. Okay, there are some good characteristic in ReLU. Okay, so I will explain that in the later sections when we actually see the structure of the AlexNet, we will learn about that. Okay. Anyways, I mean, even though there is no curve here, no curve, okay, but if the graph is not straight like this, we call that as anyways the nonlinear function, okay, and the ReLU is having some nonlinearity in x when x is exactly 0. Okay. So I mean, this ReLU is defined as the x values are defined from minus infinity to infinity, and also y is defined to be positive. Okay, including the 0 values. So if x is less than 0, their values are simply becoming 0, okay? But if x is larger than 0, it becomes the straight line, okay? Y is equal to X, that is the graph for this value, okay? So this is another form of representing this type of functions in one line, okay? But here you may ask some questions. I mean, you have to ask some question at this moment. Do you have any questions? No? You may have to have some questions. I mean, all of the functions which is used in the deep architecture have to be differentiable, okay? But is ReLU differentiable? No. Why? Hmm? I mean, every differentiable functions have to be differentiable in every x, okay? And differentiability means every function, their curves have to be smooth, okay? Smoothness is uh, the characteristic for judging if the function is differentiable or not, okay? But is that smooth? No, okay? But how then this function is used in the deep architecture? Okay, I mean, actually, I mean, this is because, in practice, in PC, it is also very hard to define the point which is exactly zero. Okay, so in practice, the value is used inside the deep architecture. Okay, but how to say, it is hard to the value is used after the convolutions, but when applying convolutions, it is hard to get exactly zero values as the output. Okay, so in practice, there's no practical issues, even though we use this type of nonlinear functions inside the deep architecture. Okay. Okay, but this ReLU is having some good characteristics, better characteristics compared to this tangent hyperbolic and sigmoid. Okay, that's why we are using this ReLU. Okay, and this is the overall CNN architectures. So if the input image size is 28 by 28, and this is denoting the convolutional filter kernels, and we can define our own output channels as we learned. Okay, so and also we can also control the output channel size. Okay, by controlling the filter kernel size and also the stride and also the zero padding number. Okay. Anyways, we can get some intermediate responses, and also by controlling stride or others, we can reduce the output sizes. Okay, this is denoting the CNN operation, and also we can also use some pooling operation here. Okay, anyways, we can define some convolutional layers here, and the objective is uh, I mean, not objective, but anyways, we are tending to reduce the 2D signals, okay? Instead, wanting to increase the channel numbers, okay? And eventually, we are wanting to make these output signals into the one-dimensional signal, okay? From the 2D to 1D, we are applying convolution operation and pooling operations, okay? And after that, we are actually doing some flattening. Okay? What flattening means is if the final layer's output is in this dimension, then we are wanting to make it into this number of this dimensional, the vector. Okay, this is the three-dimensional array, but we are rearranging the each element of the three-dimension array into the 1D vector. Okay, that is called as the flattening operation. Okay, quite intuitive. Okay, so here you may see 1 by 3,136 dimensional vector. Okay, and after applying several layers of the convolutions and poolings and activation layers, what you want to do is you are eventually wanting to make them into one-dimensional vector and want to apply some linear operation. Linear operation means this type of operation, okay? Because the inputs are now becoming one-dimensional signal, okay? You can now apply this type of simple linear operation to transform these one-dimensional vectors and eventually want to map them into uh, this type of 10-dimensional vector. This is 10 here because their targeted classification data set is having 10 classes, okay? So anyways, you want to map them into n-dimensional vector where n is the number of classes, okay? So this is the original CNN architectures which was proposed for the image classification tasks, okay? Are you guys following that? Okay. And we normally call this first part as the convolutional layers, okay? Because mainly they are composed of convolutional layers and pooling layers and activation layers, which are mostly processing the 2D signals, okay? And the later part is called as fully connected layers. You will see this part is also same as MLPs. We will learn about MLPs next time. Okay, MLPs, they are mostly the deep architectures for processing one-dimensional vector signal. Okay, so later, after applying the convolutional layers, we do flattening and then apply fully connected layers, which is same as MLP, to transform one-dimensional vectors into 1D vector that represent the the probability vector for 10 n classes. Okay. Okay. And all the operations here are differentiable. Okay. So you can train overall CNN architecture's parameters, okay, using the gradient descent algorithm, okay, when given the data, okay. Are you guys understanding that? Okay. Okay, this is end of this lecture. And next time we will see not here. So we will learn about the PyTorch library and we'll see how we can implement the concepts we learned today. Okay. And also we will start from linear regression, which is the simplest form of machine learning algorithm, which is actually implementing this type of functions, which is the simplest linear function, okay, that can map data x to the y. We will learn about how we can implement this simplest function using PyTorch. And then we will learn how we can implement multi-layer perceptron MLPs that I mentioned today. This is stacking multiple linear functions. Okay? And we will learn how we can implement these MLPs using PyTorch. And eventually we'll learn how we can implement these CNN architectures using the PyTorch library. Okay, okay. That's all for today. Okay, and see you next Monday. Thank you.